Dear students, friends, in the last class we have completed up to polar diagram. There itself, drag and lift chapter is completed. That is part 1A. Now we will go to the second part 1B under flow around submerged bodies. Unsteady flow. Just we will glance whatever you have studied in fluid mechanics 1, steady flow, uniform flow, non-uniform flow, etc. we will come across. In this particular article, we will come across with respect to steady flow and unsteady flow, because the title itself is unsteady flow. Steady flow is the one in which the fluid characteristics like velocity, pressure, density, etc. at a point or at any point do not change with respect to time is known as steady flow. That is del u by del t x naught y naught z naught is equal to 0. Similarly, del v by del t is equal to 0. Similarly, del q by del t, that is discharge, is equal to 0, etc. Where x naught, y naught, z naught is a fixed point in a fluid field where their variables are being measured with respect to time. What is unsteady flow? It is opposite to that. It is the type of flow in which the flow characteristics such as velocity, pressure, density, discharge, etc. at any point do change with respect to time. Change with respect to time. Whereas steady flow you have studied do not change. Here it is changing. Means just you have to put not equal to 0 for all these parameters. Del u by del t x naught y naught z naught is not equal to 0. Similarly, del p upon del t x naught y naught z naught is not equal to 0, and so on. Here also, where x naught y naught z naught are the fixed points, where x naught z naught y naught are the fixed point in a fluid field where these variables are being measured with respect to time. Okay. Now, different types of unsteady flow. Definitely, in case of unsteady flow, from the point view of engineering point of view, of course, we should study unsteady flow as this flow associated with change in the variation of velocity and momentum. Since change in the velocity and momentum is associated or involved, the problems become little bit difficult to solve. There are different types of unsteady flow, namely non-periodic unsteady flow, periodic unsteady flow, etc. We will see one by one. Non-periodic unsteady flow. As mentioned above, one example of an unsteady flow is a non-periodic flow. An example of when this would occur is when you turn off a valve. Generally, this type of problem does not need to be analyzed. However, if the valve were to be turned off really fast, water hammer would result. Water hammer is a force that travels through a fluid when it suddenly stops. What is the phenomenon of water hammer? We come under water hammer in detail ahead of these classes. You have probably heard that you have used an old shower and turned the water off fast. Off fast. You will hear the pipes bang. This can be a real concern sometimes, since if the force is large enough, the plumbing system could be damaged. That means due to high pressure developed due to water hammer, pipe may get bursted or damaged. Periodic unsteady flow is another type of unsteady flow that can occur in a periodic flow. A periodic flow is based on a flow change that has a pattern that will always repeat. They will repeat again and again and again. That is periodically. This makes this type of flow easy to represent with a time equation. An example of this type of flow occurs inside your car's engine. As your car runs, an air gasoline mixture is injected into a cylinder. This cycle continuously repeats, allowing the engine to develop the power needed to move the automobile. This is a very good example for periodic unsteady flow. Random unsteady flow. Apart from non-periodic and periodic, random. Finally, random flow is the hardest type of unsteady flow to analyze because of the fact that it is random. Since it is random, you generally won't be able to write a time equation to allow you to analyze the problem. That is the difficulty we face. That's what I mentioned at the beginning itself, that unsteady flow usually associated with change in velocity and momentum, that is variation in the variables. That's why the problems associated with this are difficult to solve. This type of flow occurs in turbulent flow but is normally absent in laminar flow, which you have already studied in FM1, only in case of turbulent flow. As a result, if the flow is turbulent, you can expect that there will be random unsteady flow that will affect the results of your analysis. That's why we take flow through openings under varying head. This is a good example of unsteady flow. Case 1. Time required for emptying a tank through a small opening. The tank can be emptied by using various devices like orifice, mouthpiece, or even a piece of pipe which is attached at the bottom of the tank as shown here. Consider a tank of uniform cross-sectional area containing some liquid and having a small opening at its bottom as shown in figure here. As shown in figure at the bottom of the tank. Let capital A be the cross-sectional area of the tank. Small a is the area of the orifice which is fixed at the bottom of the tank. H1 is the initial head or initial height of liquid in the tank. H2 is the final height of liquid in the tank. H2, this is H2, this is H1. T is equal to time in seconds, which is required to bring the level from H1 to H1 to H2. What is the time required? Okay, this small h is the head at any instant above the device. Let it fall by small amount dh in time dt. This is also small time. Let small h be the head above the device. Let it at any instant, let it fall by an amount dh in time dt seconds. In dt seconds. Therefore, discharge through the orifice in a small interval of time dt becomes dq is equal to coefficient of discharge multiplied by area multiplied by theoretical velocity into time. That's why CdA root 2gh multiplied by dt, which you have already studied in Fluid mechanics 1. Equating 1 and 2. We get this minus a dh. How we got the area in plan in the tank. Let us go back here. In this case, let us here h is the height above the device, dh is the small fall in time dt seconds we have said. Let us consider now the area in plan of the liquid surface, and dh is the fall. That means water leaving the tank is equal to a dh. Why minus sign is assigned? Because as the time increases, h decreases. As the time increases, water will let off, therefore h decreases. That's why minus sign is used. That is equation 1. dh multiplied by a is equal to water leaving the tank. Okay, this is equation 1. Coming to this slide, this is equation 2. In the same time dt second, the discharge through the device is given by CdA root 2g dt. Now we can equate these two equations. Minus a dh, where a is the area of the tank, cd small a root 2gh into dt, where small a is area of orifice, h is the head above the orifice, dt small time. Therefore dt, because we are required to calculate the time to empty the tank. First let us find out for small amount. dt is equal to minus a h to the power of minus half dh divided by cd a into root g. Time required for emptying tank through a small opening is continued now. Time taken capital T to lower the level from h1 to h2 is calculated by integrating the above equation between the limits h1 and h2. Therefore, here you can see T is equal to h1 to h2 minus a h to the power of minus half dh divided by cdA root 2g. That is equal to, take out the constant outside, minus a cdA root 2g. This h to the power of minus 2, when you integrate with limits h1 to h2, you will get minus a divided by cdA root 2g h to the power of half divided by half h1 to h2. So in mathematics you must have learnt integral x to the power of n is equal to x to the power of n is equal to x to the power of n plus 1 divided by n plus 1. That's why here we get h to the power of half divided by half h1 to h2. Therefore this 2 will come to the numerator, minus 2a divided by cdA root 2g h to the power of half h1 to h2. That becomes minus 2a divided by cdA root 2g minus of, in order to take care to get the plus sign, instead of h1 minus h2 we will write under the root h2 minus h1. Therefore it gives the equation 2a multiplied by root h1 minus h2 divided by cdA root 2g. Suppose if the tank is to be emptied completely, then it is obvious h2 must be equal to 0. Therefore in the above equation, in this equation, if we substitute h2 is equal to 0, we will get 2a root h1 divided by cdA root 2g. Okay, we will stop here. We will continue in the next class.